what is this Root Locus? So Root Locus is, if I want to put it very simple, Root Locus is a method that shows the location of the poles of a transfer function. Which transfer function? The closed loop transfer function, the one that we really care about. It shows the location of these poles as one parameter in the system, which could be a gain or anything that you can change. As it changes, it shows the effect of that parameter on the location of this closed loop transfer function poles. We learned that the behavior of a system depends heavily on what? The location of these poles, right? If any of them is on the right-hand side of the imaginary axis, means the system is unstable. If a few or one, typically not two of them, are on the imaginary axis, means you have sustained oscillation, the system is marginally stable. But if everything is on the left side, the system is stable. Now, how fast the system would respond, it depends on the location of these poles with respect to the imaginary axis on the left side. The further away they are from the imaginary axis means the exponential terms for them in the response would decay and die faster and vanish faster. Okay, so if you want faster responses, you want to move these poles away from the imaginary axis, right? So we'll learn about that. Now we want to see that how is the effect of changing again a parameter on the location of these poles. We learned that we cannot choose any number we want for a gain in the system, right? In the previous chapter, in the Routh-Horowitz method, I guess we learned that only for a range of some parameter, let's say k, in a transfer function, the system could be stable, right? And when we move it, it moves the location of the closed loop poles. So we want to know what ranges and how it would affect the location of them with respect to the imaginary axis. So this is a very important tool which help us design our controllers. And the idea is, can we just, by changing the gain, bring the poles to wherever we want? Is that a possibility? If that's a possibility, then all we have to do is to tune again and get the behavior of the control system that we desire. If not, then we're gonna see in the rest of this chapter that we're gonna add something called a compensator. Okay, so we're gonna add a compensator, and there are different types of them. The ones we study in this chapter are lead lag and lead lag compensators. So we're gonna add them as well, and not only they have a gain, they also have a zero and a pole that we can move. This idea was developed by Evans, and this is a graphic way to look at the location of closed loop poles based on a gain. So let's get started on this method. So here we imagine that we have a system with a feed-forward transfer function g and a feedback h. The closed loop transfer function is, of course, we know it's going to be g over 1 plus gs, assuming that this guy is negative. And of course, the part that we care about is the denominator, which is 1 plus g times h, right? The places that this denominator is equal to 0, we call them what? We call them the poles of the transfer function. So the idea is concentrating on the poles of the transfer function, or find those values of s for which this equation on the left is valid, 1 plus gh equals 0. If we take 1 to the other side, then gh should be equal to what? Negative 1. And if we write negative 1 in terms of complex numbers using the Euler formula, you know that negative 1 has a magnitude 1, and what is the angle for negative 1? Yes, that's pi, right? Or pi plus any integer multiple of 2 pi, correct? So that has, if you use the Euler formula, you definitely see that this guy here, 1 times e to the I pi plus 2 pi k, if you expand it, it is going to be equal to negative 1. Let me just, in case you forgot complex numbers, let me show you. So I just write the pi first. So 1 times e to the I pi, that is equal to what? By the way, that is 1. Still need to work on my handwriting using a software, because it's not as easy and convenient as a whiteboard. So according to the Euler formula, this is 1 times what? Yes, e to the theta in general, I theta is what? Is cosine of theta, so it's cosine pi plus I times sine of pi, right? And we know sine of pi is 0 and cosine of pi is -1, so it is going to be, the whole thing is going to be what? -1. And we know from complex numbers that when we add to the argument any integer of 2 pi in general, this is not going to change, right? Because this is going to be like cosine of pi plus 2 pi k, and this is going to be sine of pi plus 2 pi k, and since sine and cosine have a period of 2 pi, then it's not going to change the value of the sine and cosine, so you're going to get the same thing, okay? Now, going back, so now, if you look here in this area, so we know each complex number has a magnitude and has an angle. So what is the magnitude? Yes, the magnitude of the pole, the magnitude of GS at that pole should be equal to what? 1. And what should be the angle? Yes, pi plus 2 pi k. So you're going to get these two equations that you're going to see down below. That the magnitude condition at the pole is the magnitude GH at that point is 1, and the phase, the angle of GH at that point is what? If you factor out pi from this top guy here, pi, if you factor out pi, which is 180, it's going to be plus minus 180 times 2k plus 1, where k could be an integer number, right? So these two are the important thing that all the Root Locus method is developed based on: angle condition and magnitude condition. Now, let's say G times H, which is the main guy here, the thing that we have to find the magnitude and the phase for, let's say we can write it in terms of a rational function like this. So let's say this is G times H. So when we say 1 plus GH is equal to 0, this is G times H. So it has a gain, that's the gain I said, the one that you can tune, you can change, and then a product of a bunch of zeros from Z1 all the way to Zm, and then what? In the denominator you have a bunch of poles from P1 all the way to Pn. So Z's are the zeros of the transfer function, P's are the poles of the transfer function, of course with a negative sign, and K is the gain of interest, the one that we want to tune. Okay, so now using this new notation for Z's, P's, and K's, how can we rewrite these two angle and magnitude conditions? Well, so let's say S, or S star, is an actual pole of the transfer function. It's an S value for which this equation is valid, okay? So if we plug it here, what happens? So if we have the S in this equation, what happens to this magnitude condition, right? So this term has some magnitude, right? Because Z is a fixed location. Z is the zero of this transfer function G times H. So it's a fixed known number. Z1 is known, Z2 is known, Zm is known, all the way to what? P's. So these are all known, right? We'll see in an example right in a minute. But these are all known. The one that we need to find the relation between what? S and K. What relation exists between these two guys? So now, if I say the magnitude of S plus Z1, let's give it the notation. So the magnitude of S plus Z1 for any arbitrary S If I give a notation to that and I call it what? A with sub j, right? So if it's z sub j, the jth zero, the magnitude of that, I call it what? A sub j. And then the magnitude for s plus pi, the one in the numerator that you can see, all of these guys, I show them with what? B sub I, right? Correct? So then what do I get from this equation? What do you think? Or from this one, doesn't matter. The magnitude of this guy in the box here, the magnitude of this guy in the box should be equal to 1. So k is just a scalar, and we know from complex numbers that the magnitude of a scalar is the scalar itself. So it's just going to be k. The magnitude of s plus z1, we call it what? So it's going to be k times, if I want to get the magnitude of gh, it's going to be k times what? We learned we call the magnitude of s plus z1, which is a complex number in general, a1. The s plus z2 is going to be a2 all the way to what? A sub m divided by. Magnitude of s plus b1, we call it what? S plus p1, we call it b1. S plus p2, we call it b2 all the way to b sub n. This magnitude should be equal to 1, right? So we rewrite this magnitude condition into an equation like this, and that's what you see over here. Okay, so that's the magnitude condition rewritten using these new notations. Also, what about the angle conditions? The condition, I'm sorry. So it says the angle of g plus a should be plus minus pi times 2k plus 1. How do you get the magnitude of g plus h? Well, g times h. G times h is this guy in the box. What is the phase of this? What is the phase of that? So if you remember from complex numbers, the phase of a rational is what? It's the phase of the terms in numerator minus the phase of the terms in denominator, right? So let me show you one example very fast before I go back, because I want to make sure that we are all on the same page. So here, let's say I have 2 times I plus 1 divided by I minus 3, right? So let's call this z. It's a complex number, something like this, right? And somebody says, okay, what is the magnitude of z? So we know from complex number, this magnitude is what? The magnitude of all terms in numerator divided by the magnitudes of the terms in denominator. What is the magnitude of the terms in numerator? 2 is 2, magnitude of 2 is 2. What is magnitude of I plus 1? What is it? So let me write it. It's the magnitude of I plus 1 divided by the magnitude of I minus 3. So what would you get? So that's 2. What is magnitude of I plus 1? Yes, that's the square root of 1 squared plus 1 squared. And what is this? That's the square root of 1 squared plus negative 3 squared. Right, so what would you get? You're going to get 2 square root 2 divided by, that's the square root 10. Right, so that's what you practiced in your complex numbers. Now, if somebody says, okay, what is the phase of z? You say that's the phase of number 2 plus the phase of I plus 1 minus the phase of I minus 3. And what is the phase of 2? We know a real number has no phase, right? So that's 0. What is the phase of I plus 1? That is arctangent of the imaginary coefficient minus divided by the real coefficient, so 1 over 1, minus arctangent of what? The imaginary number, which is 1, divided by the real number. Okay, so it's going to be this. So this is how we find the magnitude and the phase of a real number. And if you forgot again by any chance, you go back under modules and you go back to the previous chapter lecture we had, stability analysis of LTIS systems. The first 2 slides of that are a review of complex numbers. So if you come here, you can see the definition of magnitude and phase, okay? And that Euler formula that we have used, you can refer to this, and hopefully this one give you enough info. If not, you can always come back and use this definition. So I write the rule that we use a lot. So magnitude of Z1, where Z1 and Z2 are complex numbers, over Z2 is magnitude Z1 divided by magnitude Z2, and phase of Z1 divided by Z2 is what? It's phase of Z1 minus phase of Z2. Okay, so these two we're going to use a lot in this section and from this point on, so hopefully you remember them. Okay, so now remember that all of these Z's and P's in general can be complex numbers, okay? So they are not always real numbers. Why? Because we broke down everything into linear terms, correct? So if we had a term like this, s squared plus 1, you cannot write it in terms of linear terms unless you write it as what? S plus I times S minus I, correct? Because this guy has no real root. So if you want to write everything in numerator and denominator as a product of only linear terms, then some of these Z's or P's can in general be what? Complex numbers. So now, we learned that the magnitude condition will be what? K times A1 all the way to AM divided by B1 all the way to Bn equals 1. And then, if we call the angle of the numerator terms S plus Zi, each one of those 0 terms, if we call them theta j, and the angle arg, or angle argument, for S plus pi, we call it phi I, then, since as I said k, the constant k is a real constant, since that term does not have a phase, so it's going to be summation of all thetas minus summation of all terms in denominator, all phi's, should be what? Plus minus pi times 2k plus 1, okay? So these are the equations that we have to satisfy for point S if it is a closed loop pole. These two conditions for it must be satisfied. And you can see a visualization of these A's, B's, thetas, and phi's in these two pictures, right? So if S is a point that we say this is a closed loop pole, and these are P's and Z's shown in this picture, the P's are all shown with a cross, and the Z's are all shown with a circle. So in this case, like you have 4 P's and 1 Z. Then, as I said, A is the magnitude of S plus Zi. So let's look at Z1, for example. So what is this vector here? What is this guy here, if you know? The one that connects Z1 to S, right? This vector. Let me show you an arrow also. So this vector. Let's see if I can use a vector. So it's the vector that connects point negative Z1 to S. We know complex numbers are exactly treated like vectors. So the vector that connects this point to this point is the end point minus the beginning point, right? So it's S minus what? negative z1, so it's what? S plus z1, one of the terms in the numerator, right? So this vector that connects negative z1 to s, this vector has a magnitude, and that magnitude I showed with what? Yes, with b1. And then each one of these poles, when they are connected to s, each one of them, the vector that is connecting, the magnitude of that I'm showing by what? By a's. A4, A3, A1, right? A1 is the one between negative P1 to S. A2 is between negative P2 to S, and so on and so forth. And then the angle of these guys are called what? Thetas or phis, right? So for A's, for zeros, we call them thetas, and for the denominators, we call them phis. And that's what you can see over here, right? Let me make sure that I'm not making a mistake, because it seems like I am making a mistake. Because in not making a mistake, but there is a contradiction in notation, because as you can see here, phi is the angle that connects z to s, and z's are in the numerator. So if we want to stay consistent, we have to change here. We have to be very careful about notations, otherwise I might make you confused. So that's how it should be. Okay? Now that we have seen some notations and terminologies, it's time for me to show you how to draw the root locus, which is again the location of the closed loop poles as this parameter k is changing. We are looking for something like this, okay? So we're gonna draw a plot like this, where parameter k is changing and the location of the closed loop pole will follow this curve as k changes, okay? This is the ultimate goal of this section, this lecture here, and then we're gonna talk about how we can use that, right? And one last thing, again, you might wonder, why are these points negative z's, negative p's? Didn't you say that z's and p's are the zeros and the poles of the transfer function? No, I said z's and p's are what? Is zeros and poles of g times s, but with a negative sign, right? If you look at these, all of these guys are positive instead of negative. Right, so this s plus z1, as I said, can be written as what? S minus z1. When you set this equal to 0, where is the location of the 0? Yes, negative z1. And when you set a pole term equal to 0, s is what? Negative pn, okay? So the z's and p's are the zeros and poles, but with a negative sign. Okay, so the location of poles and zeros, they all have these negatives in them. Okay, one last thing before we start the procedure for drawing the root locus is, here we are focusing not only on G or H, we are focusing on the product of G and H. So you might wonder, well, what happens, so this whole thing here, this k times s plus z1 all the way to zm divided by s plus p1 all the way to pn, that's the product of g and h. And you might wonder, well, what happens, because g and h could be rational, they are rational functions, right? They have ratios. What happens if like g has a 0 and h has a pole that they are exactly at the same location? Well, when we multiply, they cancel out, okay? Similarly, if g has a pole at the same location that h has a 0, right? So any similar pole 0 combination between g and h would cancel out, and they will not so contribute to the root locus. Okay, so let's go back. So how do we draw that graph I just showed you? So this is what we do. First of all, one of the most important thing that many times the students might just neglect is we rearrange this equation 1 plus gh equals 0 into a form like this, where K always appears in the numerator, okay? Not always when we multiply G by H, K, the parameter that we can tune, appears in the numerator. Sometimes it does not. I give you an example in a minute. Then we have to rearrange this 1 plus GH equals 0 in a form that K appears in the numerator, okay? So K is a real value, is a real coefficient, real gain, and it's never complex, it's always a real number which should appear in the numerator. So let me show you a case that this guy is not always appearing. So let's go through an example together and see what we should do about it. So let's say G is equal to S plus 1 times K times S squared plus, or let me write it as linear terms, S plus 2 times S plus 3. And H is equal to S divided by S plus 1 times S minus I times S plus I. Okay, or if you want, I can make this like, yeah, I guess that's okay. That's good enough. So let me show you when such thing happens. So when now you say 1 plus GH is equal to 0, well, first thing you might notice is this S plus 1 and this S plus 1, since when you multiply G by H, that's in the numerator, this is in the denominator, they would cancel out, okay? So that's 1 S plus 1, that 0 or pole at -1 is not going to do anything for us. So now if you do it, it is going to be 1 plus what? It's going to be 1 plus S over K times S plus 2 times S plus 3 times S minus I times S plus I is equal to 0. By the way, notice that the product of these two is S squared plus 1, but as I said, we have to break down every term in numerators and denominators to linear terms. We should not leave anything as a quadratic, even though the roots are complex, okay? So now if you look here, this is not the form that we wanted because K is in the numerator. So what do? Well, we take a common denominator, cross multiply. So if we do that, you're going to get what? You're going to get K times S plus 2 times S plus 3 times S minus I times S plus I plus S should be equal to 0, right? Because when we take common denominator, right? When we take common, let me go up. When we take common denominator, this term is in the denominator, but this denominator term cannot be 0. The numerator has to be 0. Good? So we are down to this one. This numerator has to be equal to 0. Okay, now what? So as I said, K should be in the numerator. So what do we do now? So if we divide both sides by S, it's going to be what? So we are dividing now this equation only, this numerator only. We divide both sides by S. So it's going to be K times S plus 2 times S plus 3 times S minus I times S plus I. The whole thing divided by S plus 1 is equal to 0, and now it is the form that we wanted. 1 plus a rational function equals 0, where that rational function has k in the numerator. So this is what we focus on. And if you say now, what are the z's and what are the p's? So z1 is what here? Clearly you see it's 2, because they were all z plus, s plus z's and s plus p's. So z1 is 2, z2 is 3, z4 is negative I, and I jumped something. z3 is negative I, and z4 is positive I, right? And what is p? There is 0 here, so this guy is p1. What does it mean about the location? It means that the zeros are at -2, -3, the roots of this. Negative I and positive I and negative I, and the pole is at 0. Okay, we barely see ever something like this. Typically the poles are much more than zeros. But just wanted to tell you what would happen if we have such a case that the gain k, the one that we are interested in, does not appear. When we write 1 plus gh equals 0, this does not appear in the numerator. Then we have to rearrange everything to bring it up to the numerator and make it again 1 plus something equals 0. So we're going to focus on that one maybe. Not maybe, for sure. Okay, now going back. So that's the meaning of item number 1. Now items 2 and 3. It says locate the poles and zeros of the GH, this term only, on the S-plane. Show poles with crosses and show zeros with circles. The root locus branches start at the poles and they would end at zeros. For what values of k? When k is 0, you start at the poles, and when k goes to infinity, they end up at zeros. First of all, how many branches of root locus would you have? As many as the poles, right? So if you have n p's here, you see the poles are n p's, then there is n branches of root locus. One other thing that really helps us is root locus is always symmetric about the real axis. So what we are drawing here is everything is in the imaginary plane. We have a real axis and an imaginary axis. So root locus is always drawn like what? Any complex plot. And it is always symmetric about the horizontal or the real axis. Okay? So stage number 2 is you locate the poles and zeros of GH. So let's do all of that with one example, because ultimately we want to do this example together. Okay? The goal is to do this example as the first example for us. So let's focus on this example as we go through step by step. Let's work on this example. So it says, draw the root locus for the system below, and we draw it on the paper, which here is of course software OneNote, and we also gonna see there is a command in MATLAB that can easily do it for us, and then we focus on gain k and do a bunch more. So the thing that we are focusing right now here in this example is this guy here. So this one is g of s, and h of s is equal to 1. And the good thing for us is the k that we care about is in the numerator of g. So when we say 1 plus gh equals 0, k is in the numerator, so we do not need to rearrange anything, okay? So if we focus on this example and go to OneNote and start here. So when we say 1 plus gh, it is 1 plus k over s times s squared plus what? 4s plus 5. That's g times h, which is 1. This is equal to 0. And then the only thing we focus on is this guy here, g times h. Okay, this one. That's all we would focus on. So now, where are the poles and where are the zeros? So clearly you see there is no linear term in the denominator, so there is no z. We do not have any z, but we have some poles. The first pole here is at what? The first pole here is at, wow, what is going on here? Excuse me, I'm still not the best at doing this, so bear up with me. So it's, wow, there is something going on, which I don't know. That's okay. Let me write something somewhere else. So P1 is at 0. There is no z. What about this? We have to bring down everything to linear term. Does this guy have real roots? If we form the discriminant, it's 4 squared minus 4 times 1 times 5, so it's negative 4. So this guy does not have real roots. It actually has complex roots, and if we find them, P2 and 3, which should always be complex numbers, should be what? Negative 2 plus and minus, so negative b prime plus minus b prime squared minus ac, which is negative 1, so you should get negative 2 plus minus I, right? And you can always check it with MATLAB, but I don't think we need to. So if we just say roots of 1, 4, and 5, yes, they should be negative 2 plus minus I. So we have 3 poles, no zeros, k is in the numerator, life is good so far. Now it's time to plot them in the complex plane. So now this is what we do. So now we draw some axes, and let's see if I can use these tools properly. Or maybe I go to a new plane, a new page to save some space. Here, so that's one axis, and then we use another one like that. Okay, so this is the real axis, and this is the imaginary axis. So it says draw the poles with crosses and zeros with circles. We don't have zeros, so life is good, but we have one pole here at 0, and then we have a couple of poles. If this is negative 1, negative 2, negative 2 plus I, and negative 2 minus I, right? So this is P2, and this is what? P3. So we show the poles with crosses. Again, if we had a 0, then we would show that 0 with a circle, but we do not have it in this case. And as I said, the plot that we'll do is always symmetric about this real axis. How many? And it has several branches. How many branches? As many as the poles. So we're going to have 3 branches for this root locus. Good. Let's go back. So now it says find the root locus on the real axis. The complex conjugate poles and zeros have no effect on that. The only thing is, if you choose any point on the real axis, if the total number of real poles and zeros to the right of that point is an odd number, then what? Then that point belongs to the root locus on the real axis, otherwise it does not. So root locus, as I said, it has several branches. Some branches are what? Only on the real axis, like this picture. Some of them are completely 2D. They are in the plane, but some of them are only on the real axis. So we want to know, out of this infinite real axis, which part of it can a Root Locus branch stay on or coincide with. So it says, go back here, and then if there are complex conjugate poles or zeros, forget them. They have no effect on this. The only thing that has effect are the real poles or zeros. Here we only have one real pole, no real zero. Good. Now it says choose any point you want on this real axis, let's say a point here. If the total number of real poles and zeros to the right of that is an odd number, that point belongs to the root locus. So if I look at the right side of this point, how many real poles and zeros total I see to the right of that? Only one. And one is what? An odd number. So yes, that point actually does belong to the root locus. What about here? The same thing. To the right of that, there is only one pole and zero total. What about this? The same. So all, if I look here, all of this portion, all of the negative side of the imaginary axis does belong to the root locus. What about the point here? If I do a point here, how many total real zeros and poles are on the right side of it? None, and none or zero is an even number. So any point on the right side does not belong, okay? It does not belong. And you might wonder, it says the complex numbers, the complex poles or zeros, they do not have any effect. Why? Because there is always two of them on the same vertical line. They are always complex conjugate. So if I choose a point here, and if I count them really, we said only count the real ones, but if you even count the complex ones, how many do you have here? Yes, 1, 2, and 3 to the right side. So still what? It was an odd number here, it was only 1, but once you pass it, you go from 1 to what? To 3. If there is another couple, it's going to go from 3 to 5. And so since it's all odd, then it does not affect the location of the root locus. So the complex don't care about them. Let me demonstrate that a little more on these plots here. So if you look at these plots, so let's look at some of these. So let's look at this case here, the top one. So this case, which is quite similar to our example, except for all poles are real. So if you look here, there are 3 real poles, one at 0, 2 negative ones, to negative numbers, and where on the real axis does belong to the root locus. So if I choose any point on the right side of the imaginary axis, like here, how many to the right side, how many real poles and zeros are to the right side of this point? None, 0, so it's an even number, so that does not belong. Now if I come here between the first pole and the second pole, how many points are to the right of it? How many poles and zeros, real poles and zeros, are to the right of it totally? Yes, only 1. So this area does belong. If I come here, what happens? Now to the right of it, there are 2, and 2 is an even number, so this area does not belong. And if I pass here, now again to the right of it, you have what? 3, so this area does belong. Yeah? Let's look at the case with zeros. Look at here. Is there a complex case? Yeah, this is good. This last one. So here again, on the right side, no zeros or poles total, so it doesn't belong. Here, there is 1 pole only to the right. It's an odd number. That's good. If I come here, now what? I have 2 total to the right, so it does not belong. If I come here, now what? I have 3 total, 1 0 and 2 pole, 3 total to the right. So this area does belong, and this area does belong. And if I come here, what happens? It's going to go 4, and 4 is an even, so this area does not belong, right? So we can practice it on these cases here. You see here, there is none, then you jump to 3 on the right side, so this area belongs. And since when you pass here a complex pole, it does not count because you go from 3 to 5. This whole area belongs to what? Belongs to the root locus, okay? So hopefully I could make this item number 3 understood. Now what? So now it says find the angle of the asymptotes of the root locus and their intersection point. Again, what does it mean? So if you look at the root locus plots, some of these, not some, all of these plots, the one that have asymptotes, that asymptote can have some angle and then an intersection point. Let's look at this case here. If you look at this case here, you see that I can draw an asymptote like this, and I can draw an asymptote like that, right? And they have some angles. Oh. They have some angles, and then these asymptotes have what? An intersection point. Or let's look at, let's say, a case maybe here again. You can see that. So there is asymptote here, and there is an asymptote here, and there is an intersection point. There is a similar thing here that you can see. There are so many different cases, okay? You can see there is asymptote to the branches, some of them, and there is intersection point. Now, where are they? Because when we draw them, it helps us a lot in drawing the rest of it. So it says, what are the angles of the asymptotes? The angle of the asymptotes are that plus minus pi times 2k plus 1, the guy that we had here in the angle condition, that one divided by what? The difference between the number of poles and the number of zeros. So if you have n poles and m zeros, then n minus m will go to the denominator, right? And the intersection point is what? Negative of all of the p-values plus what? All of the z-values, right? Or if you bring negative to the backside of the ratio, it's negative of all the p-values minus the z-values divided by n minus m. And by the way, these p's and z's are not the actual poles and zeros. They are the poles and zeros with a what? With a negative sign. Of course, you can write this in terms of actual poles and zeros, because if you bring this negative and multiply it by the whole thing, this becomes like this. Negative of them and positive of this, right? And let's take care of this negative. So we can write it like that. And then, now what is this? Summation of all negative p's. This is what? Summation of all poles, actual pole locations. And what is this? Minus, instead of this plus, you can write it as, if you want, you can write it as minus minus, right? Minus minus pole, minus zeros. And then this negative is what? Negative all z's. Yes, this guy here. So this all negatives is summation of the poles. All this is summation of what? Summation of all zeros. Okay. So if I want to rewrite this in something better understood, I say the location of the asymptote intersection is summation of all poles minus summation of all zeros divided by n minus m. I can write it like that as well if that makes it easier to understand. But here these are actual poles and actual zeros, no negative. And we're going to practice it right now. So now if I go back to this example, so referring back to these p's and there is no z, so where is that location now? Where is the intersection location? So the intersection location S is what? Summation of all poles, right, minus summation of all zeros divided by n minus m. First of all, what is n? What is m? N is the number of poles, so we have 3 poles, so n is equal to 3. And how many zeros we have? None, so m is equal to 0. So first of all, we're going to have 3 branches, and then if we find the location of the asymptotes intersection with the real axis, it's going to be what? Summation of all poles, which is what? 0 plus negative 2 plus I plus negative 2 minus I. This is summation of all poles, right? Minus summation of all zeros. There is no 0, so it's just 0 divided by what? 3 minus 0. So when we add them, what happens? The i's and negative I would cancel, so you're going to get the negative 4 here divided by 3. So at which points the asymptotes would intersect the real axis? At s equal negative 4 over 3. It should always be a real number. Okay, and that real number in this case is negative 4 over 3. And what is the angle of these asymptotes? What is the angle of the asymptotes? So the angle is what? Again, if you go back, it says plus minus 180 times 2k plus 1 divided by n minus m. So plus and minus 180 times 2k plus 1 divided by 3 minus 0. If you simplify 180 and 3, it's going to be plus and minus 60 degrees times 2k plus 1 for which values of k? By the way, this k and the gain k, this and that are two different things. So this guy is the gain that you can change. This k here is what? It's just an integer number. If you don't like it, I can use another notation for you. Okay, maybe I choose another notation. I don't know what you think, but in my lectures, I showed the gain that you can tune with cap k, and this k that is simply an integer number with what? With small k. So please note that these are two different things. This k can range only on integer numbers from 0 to n minus m, and that k can be anything that you choose. So if I go back here, this k, if you don't mind, I keep my notation, but I use small k just to make sure. So small k, and small k here too. Okay, where k can go anywhere from 0, 1, all the way to n minus m, which in this case is what? 3. So k can range anywhere from 0 to 3, and if you plug in, what would you get? If you plug in 0 here, it's going to be plus or minus 60 degrees. If you plug in 1 here, it's going to be 3 times 60, so plus minus 180, which is, they're the same angle basically. If you plug in 2, it's going to be 5 times 60, which is what? 300. And you know 3, let's make sure. If you plug in 2, that is going to be 5 times 60, so that is 300. So it's going to be plus and minus 300, which these two are the same thing, right? You know, plus 300 is negative 60, and negative 300 is positive 60. So we're repeating ourselves. And if you plug in 3, you're going to get 7. So you're going to get 420, plus and minus 420. And 420 minus 360 is what? 60, right? So those are the same thing as these guys. So these angles are the same as that, and those are. So these are not going to contribute any new angle. So these are nothing new. So it's just plus minus 60, and plus and minus 180 are the same thing. They are the same angle, right? They fall on each other. So basically all angles I have is only plus minus 60 and what? Positive 180 or negative 180, doesn't matter, right? That are all angles that I have for the asymptotes, 3 angles. So now if I go here and look at this, First, at what point do they intersect? The asymptotes -4/3. Remember, here this number is 1, this number is -1, and this number was 2, if you remember, or -2 actually. And the intersect is -4/3, so if that's 1, you're looking at here. That green point is where the asymptotes are hitting each other. And what are the angles? One is +60, like that. Or let me use solid lines. And the other one is what? -60, like that. So that angle is +60, this angle is -60, and then the other one is what? 180, this angle here. This whole thing, right? So these three green guys are my asymptotes, right? My branches should ultimately fall on them as k goes to infinity. So far I have found the location of the poles on zeros. There is no zero in this case. I found the asymptotes, the angle of them, and where they hit the real axis. And with this blue line, I found the location of the root locus on the real axis. Now, part 5. It says find the breakaway and break-in points. Okay, now breakaway and break-in points, they either are on the real axis or they might occur in complex conjugate pairs. What are they? Let's first see what are they, and then the important thing is the k corresponding to these locations should only be a real positive number. That is really helpful. First of all, how do we find them? The first thing is we rewrite our characteristic equation 1 plus gs equals 0 into a form like this: bs plus kas equals 0, or in other words, we find k from that equation based on everything else, and then we take a derivative of k with respect to s. The derivative of k with respect to s at the breakaway or break-in points is equal to 0. So from this equation we can find the location of the breakaway and break-in points, and then if we plug them, the s values, if we plug them back into the equation for k, it's going to give us some k numbers. Now, not every point that we find from this equation is actually a breakaway or break-in point. Some of them are, some of them are not. How do I know which one are real breakaway or break-in points? So if I plug in the s value I found from here back into the k equation, then if the k is turning out to be a positive real number, that is an actual one. Otherwise, it is a fictitious one. And I'll show you all of that. So no worries. So first, what is a breakaway or break-in point? So if I go back here, so if you look at this example, let's look at the first one. If you look at this example, let's say I know the numbers here. So it's 0, 1, and 2, right? -1 and -2. If I find the location of where the asymptotes hit the real axis, so it's going to be 0, -1, -2, so sum of the poles is -3. There is no 0, divided by n minus m, which is 3 minus 0. So in this case, if I do it, the location of asymptote intersection with real axis is -1, which is exactly on the pole. So, and the angles are ±60 and 180, just like the examples we are solving. So if I draw the asymptotes in this example, they exactly look like this. They hit right at point -1. And let me draw the third asymptote as well for you. So these are the three asymptotes in this graph. But at what point does the actual graph, this black curve here, get off from the real axis? Here, this guy here, if you look at it, this guy is the breakaway point. This is where the root locus breaks away from the real axis. Okay, that's what we call breakaway point. Okay, sometimes the root locus can come in. Let's look at this example here. As I said, the root locus starts at the poles with k equals 0, and as k goes to infinity, it moves toward the zeros of the system. So if you look at this example, here there are 4 poles and 1 zeros. So when k is equal to 0, the root locus is, there are 4 branches. If you clearly see, there is one here, there is one here. One of them goes from this pole all the way to 0. The other one goes from this pole all the way back to infinity. So one branch is like this, and the other branch is like this. Okay, and this is one branch, and this is one branch. So there are 4 branches. Or in here, one of them is like going from this pole to 0. The other one goes from this pole to infinity. So again, at poles, this is where the k's are 0. And when k goes to infinity, you are approaching a what? 0 of the g times h. But you might say, okay, this branch is just going to infinity itself, so where is the 0? You said when k goes to infinity, you should approach a 0. I can see it here, I'm approaching a 0, but what about this branch? Where does it go? It goes to an imaginary 0 at infinity. Okay, so we assume that there is a 0, but it's imaginary at infinity. What about these cases? We are starting at 3 poles, but all of them are going to what? When k goes to infinity, this branch is just keep going, this branch is just going, and this branch is just going. Where do they go? Should I end up at a 0? Yes, but all of the zeros in this case are what? Imaginary at infinity. So if the number of poles and zeros is not equal, which most of the case it is not, whatever that we are lacking, we assume they are imaginary at what? Infinity. Let me show you one more example, and then we go back to the breakaway and break-in points. So let's look at this example here again. So one of them comes from this pole to this 0. The other one goes from this pole to that 0. But this one goes from this pole to no 0. And you might say, where is that 0? Yes, again, it is at infinity, an imaginary 0. Good? So hopefully, right now, first you know about the number of branches and where they go and where they come. Now, going back to the notion of breakaway and break-in points. So as you can see, the root locus branches at some points, as k goes from 0 to infinity, they get off the the real axis, and they get into 2D. So that point is what I call a what? I call it a breakaway point, because it is breaking from the real axis. Sometimes, like here too, right? If you look at this example. So both of my branches are breaking off from what? The real axis. So this point is a breakaway point, but then at some points this root locus might come and hit back the real axis, and it becomes coincident with the real axis, like this point, right? So you see the root locus branch, which is started at a pole, now coming back and again here hitting the real axis. So that point is what I call a what? I call it a break-in point. Okay, so that's the meaning of breakaway and break-in, right? So just by looking at them, I can find out which one is breakaway, which one is break-in. So here I have a what? A breakaway. Here I have a breakaway. Here I have none. Here I have a breakaway. Here I have both. Here I have one breakaway, and so on. Mostly you have breakaways because you have more poles than zeros, but sometimes you have break-ins too. Okay, so first it says, at which point does my root locus get off the real axis? how can I find this? Clearly, you see these points are not the same as where the asymptotes are hitting the real. They might be close to it sometimes, but they are not the same point. So I cannot just use this simple formula here. This is only for asymptotes. If I want the breakaway or break-in, I have to find from this 1 plus GH equals 0, I have to find K as a function of everything else. So I find it as a function of S. And then what? I take a derivative of that, and then I find those S locations, and then in order to make sure they are actual breakaway or break-in, I put those points I find back into K and see if the K corresponding to them is a real positive number. Okay, so let's do that for this example here. So if I go back to this example, what do I have in this example? So this is my 1 plus GH, you see it here. It's 1 plus K times this. This is equal to 0. So from here, I find K as a function of everything else. So let me come here if you don't mind. So what I have is 1 plus K divided by S times S squared plus 4S plus 5 is equal to 0. If I find K from here, I take 1 to the other side, cross multiply. Going to be negative S times S squared plus 4S plus 5. And if I expand it, it's going to be negative S cubed, negative 4S squared, negative 5S, right? So I found K as a function of S. That's the goal, this function here. Now I take a derivative of K with respect to S. So from here, what is dk over ds? I'll take a derivative of this. That's negative 3s squared, negative 8s, negative 5, right? This guy is equal to 0, and if you do that, there are 2 roots to this. So we can use the discriminant, or we can use MATLAB, negative 3, negative 8, negative 5. And the roots are at negative, this is 2/3, so it's negative 5 over 3 and negative 1. Okay, so one of them is at negative 1, the other one is negative 5 over 3. Okay, now are both of them actual breakaway and break-in points? Well, we're going to plug them back here into the K formula, right? This is K as a function of S. I plug them both here and see what K values they are giving me back. So if I look at the K values, if I plug in negative 1 in here, what would you get? You get 5, 6, minus 4, so you're going to get 2, right, in this case? Or is that right? Let me make sure. So 5, 6, 2, yeah, that's correct. And if you plug in negative 5 over 3 in here, right? Negative 5 over 3. So negative 5 over 3 cubed, negative what? What is it? 4 and 5. Negative 4 times that number squared, and negative 5 times that number, right? If you do that, I messed up somewhere. One, did I make any mistake? Negative, negative, negative. Okay, let me make sure I'm not making any mistake, because I didn't just solve this example right before coming. I just wanted to be everything real time. -3, -8, -5. So the roots are correct. This is 2/3, -5/3, right? -5/3, that's right. That is our first root. And if I plug it back into the equation for k, it's negative s squared, s cubed, -4s squared, -5 times s, and this is also positive. And if instead I plugged in negative, what was the first number? The second number was -1. So if I plug in -1 here, that should be 2. So it seems like both of them are positive. So 1.85. So this is 1.85. So both of them turn out real number and positive. So it means both of them should actually be a breakaway or break-in. And now if I go back here, is that the case? Okay. And if you look at this case here, so if we plot and look at this Root Locus in MATLAB, let me first show you the final result so that we can, by the way, the command rlocus is what you need to plot the Root Locus, and all you need to pass to it is numerator and denominator, which in our case is, if you look at here, the numerator is 1. Forget about k, it's 1. Denominator is this guy here with no negative sign, 1, 4, and 5. So it's 1, 4, 5, 0. If I look at the Root Locus of this system, which is what, again, we have to do at the end of this example, this is the Root Locus, okay? And clearly you can see that this is one point that the Root Locus branches get off, and this is another point, okay? And this point clearly you see is -1, and this point here is what? -5/3, right? So the answer is yes, both of the breakaway points are correct. So far we found both breakaway points, okay? And we have done number 5. Now, what about the angle of arrival and departure? So if you have a complex pole, you might have angle of departure, or if you have a complex 0, you might have angle of arrival of the Root Locus from those locations. Now this is just to make Root Locus more accurate when we want to draw it by hand. It says the angle of departure from a complex pole is 180 minus some of the angles from all other poles to that pole plus some of the angles from all other zeros to that pole, and then angle of arrival at a complex 0. In our example here, there is no complex 0. There is no 0 at all. So we don't need angle of arrival at a complex 0. All we have is a pair of complex poles. And so, again, if I go back to this graph that I just did for you, you clearly see here, if I draw a line here, if I draw a line tangent to the Root Locus at that point, okay, let me continue it all the way to here, this angle of the Root Locus tangent with respect to the horizontal axis, this angle is what we call what? The angle of arrival, okay? I'm sorry, departure. This is the angle at which the Root Locus branch, this green one, is departing that complex pole. And a similar thing can be done for this other one, right? You clearly see, if I draw again a tangent to the red branch of root locus at that complex pole, again, the angle between this tangent line and the horizontal axis, this is the angle of departure of root locus from that pole. Okay, so these two angles here are called the angle of departure. If I had a complex zeros where root locus come in to those zeros, then I have angle of arrival. So here we're trying to find these angles, and these are completely different things from the asymptotes, okay? These are absolutely different things. Asymptotes were these guys here. If you remember, asymptotes would hit at -4/3, like this, and then +4/3, right? So do not mix this angle of arrivals with angle of asymptotes. In this case, we found the angle of asymptotes is positive and -60, and these two on the right side are asymptotes, but these two on the left are the tangent. So let me show it maybe like this. These are the angle of arrival, angle of departure, I'm sorry, from those two complex poles. Okay, so they are completely different things. Now, how do I calculate them? This one says if you have a complex pole, the first one is 180 minus some of the angles from other poles to this pole plus some of the angles from other zeros to this pole. So in this case, if I go back, so what do I have in this case? Let me use a different color. So there is no zero, so life is good. So all I have is 180. Such a nice thing. 180 minus summation of the angles from other poles to this pole. So if I focus on pole P2, this pole, what is the angle of other poles to this pole? So if I connect pole P1 to pole P3 with dash line like this, or let's use solid line, what is the angle of the vector that connects what? P1 to P2, right? What is this angle? By the way, we measure every angle with respect to the positive real axis. What is that angle? So if I call that maybe theta 1, and then what is the angle that you draw from P3 to P2? So what is this angle? Again, we measure everything with respect to the horizontal positive axis, theta 2. So it's 180 minus summation of theta 1 and theta 2. Let me write theta 1 and 2 in a better way that you can read. And then if there were angles from zeros to this pole, then we add them. But here we don't. So what is it? Theta 2 is clearly 90 degrees. That's not hard to calculate because that vector is vertical. But this vector, in order to calculate it, we need the vertical and horizontal components of P2, which if you go back to, where was it? It's here, -2 plus I and minus I. So the real part is 2, the imaginary part is 1. So if I calculate this angle instead, this angle is tangent inverse of what? It's tangent inverse of 1/2 because the real part is 1 and the imaginary part is 1, the real part is 2, right? So theta 1 is what? It's 180 itself minus this number. Tangent inverse of 1/2, right? So if you simplify this, what would happen? These two guys would cancel out, and you are going to get tangent inverse of 1/2 minus 90 degrees, right? And what is that? If you calculate it from MATLAB, so A10D of 0.5 minus 90. I'm using A10DD to give me back in degrees, and you see it's negative 63 degrees, 63.4. So it's negative 63.4 degrees. And if I go back again to this plot, let's see if it allows me to draw on MATLAB 2. No, it doesn't. MATLAB is not as user-friendly. So if I get another line from here, so if I draw the horizontal axis temporarily here, this angle between, so that is pole P2, this angle between the tangent to the root locus and the horizontal, what is that angle? That's 63 negative. And clearly you see, because this angle is clockwise, right? Because this angle from horizontal to this is clockwise, is negative 63 degrees. Similarly, I can easily show you, if I calculate it for P3, it's going to be the opposite of that, positive 63 degrees, right? So the angle of departure from this is negative 63, from this one is what? Positive 63. And what about this guy? What do you think? Just looking at it, clearly it says when the root locus are getting off from this, it is going horizontal. So the angle of this should be what? Yes, should be 180 degrees, right? Now, is that the case? Yes. Why? Let me show you. So if I go back here, now here is a little too crowded. Let me add it somewhere else again, because this root locus explanation needs a ton of detail. So let me show you one more time, maybe. So we had one pole here, and one pole here. So it says the angle is 180 minus the angle from the other poles. Okay, so that's how you calculate it, plus the angle from other zeros, but here we don't have any zero. So what is theta 1 and theta 2? So we connect these guys to P1 like this with these vectors, and then find their angles. So one of them is this angle, one of them is this one, right? Okay, so what do you think? How could it be that it is gonna end up with 180? Yes, because if this angle is whatever it is, it was like 63 degrees, right? Actually, yeah, that one was 63 degrees, right? So that is theta 1, that is theta 2. So that is 63, this is our negative 63, that is positive 63, so this summation goes to what? To 0. So the angle of departure from the pole at 0, P1, should be what? 180, and clearly you see it here, right? That the tangent to the root locus, which is horizontal itself, the angle of that with respect to the horizontal axis is what? 180, and that is completely right. So we did go through number 6. Finally, number 8 is not a part of root locus, it's just number 7. Number 7 says, now find where the root locus hits the imaginary axis. Find the intersection points, and these are extremely important. So here, if you look, what it is asking from us is, can I draw an ellipse? Yes. I'm looking at these points. One here, right? And the other one is here. So at which points does the root locus hits the imaginary axis? Find these locations for me. Why are they important? Because K, as I said, K is increasing, right? K here is 0, and as we move along the branch, K is going bigger and bigger to infinity. So at this point, K is a number between 0 to infinity. But that number is really important. Why? Because if K is less than that number, between 0 to that number, what happens? Your poles of the transfer function are to the left side of the imaginary axis. So your system is what? Yes, stable. But if k is bigger than that number all the way to infinity, then your poles now become to what? Move to what? To the right-hand side of the imaginary axis. So now the system becomes unstable. So here is the threshold between stability and instability, right? So k at that point does matter, and the location of that point, when we find it, based on that, we can also find what? The k. So it's really important. So how do we find the location of them and then the k corresponding to those points? How do I find that? Well, one way we did in the past, if you remember, was called the Routh-Hurwitz method, right? We can look at the characteristic polynomial with k factored in it, and based on that, we can find the range k for which the system is stable. So that can give us the threshold here. And then above that, the system is unstable. So we can do it. It does not, the Routh-Hurwitz does not give me the location of the intersection. It only gives me k at that location. But here, I'll show you another way that can give you both the location and the value of k corresponding to that. And, well, you might wonder, how do I do that? Well, what do you think? At the intersection with the imaginary axis, if I call that point S, S should be what? It should be positive or negative j times what? Times some value like omega or delta or sigma or whatever you call it, right? There is no real part to that. It's only imaginary. So if this is positive I times omega, and omega could in this case be 2 point something. This one is what? Negative 2 points I, right? Or negative I omega. So if I just plug in S equal I omega or negative I omega in my characteristic equation and solve for omega, then I can find what? The value of omega, and then also I can find the value of k. Let me show you how to do that. So that's number 7 and 8 together. So in our case, in our example, what is my characteristic equation? The characteristic is this guy here, right? This one in the box. Or this one that I wrote here, the second line. These are equivalent, right? So let me write it again somewhere else for you. So my equation is this. That 1 plus k over s times s squared plus 4s plus 5 is equal to 0. This equation is valid for any point on the Root Locus, any point, including the intersection with the imaginary axis. So now this is what I do. I first cross multiply to make life easy and get rid of this term. If I do that, I'm going to get s cubed plus 4s squared plus 5s plus cap k is equal to 0. That is my characteristic equation, right? This one here. This is my characteristic polynomial. Now, there are two ways I can handle it, as I said. One is, in this equation for s, I plug in what? J times omega, or I times, let's not use J, I times omega, or negative I times omega, doesn't matter really. So if I plug it here, what do I get? It's going to be I omega cubed plus 4I omega squared plus 5 times I omega plus k is equal to 0, right? So that's what I have. Okay, and let's simplify this a little bit. As I know, you love complex numbers. So what is this? It's going to be I cubed omega cubed plus 4I squared omega squared plus 5I omega plus k is equal to 0. Now, based on complex numbers, we know I squared is what? Negative 1, and I cubed is negative I, right? We know that. And so, now if you see, this is negative I omega cubed, this is negative 4 omega squared, this is 5I omega, this is k. Two of the terms have I, two of the terms don't. These two terms they have I in them. And these two terms do not have I. Right? And summation of the whole thing is equal to 0. What does it mean? It means the terms without I, summation should be 0, which is k minus what? 4 omega squared should be 0. And then if I factor out I in these two guys, what would you get? 5 omega minus omega cubed. Right? This guy should also be 0, right? When I factor out I in these two terms with I in them, you're going to get 5 omega minus omega cubed. Right? Or if you want, let me write it this way if it helps any better. So I write this a little more organized. So it is going to be k plus 4 omega squared plus I times 5 omega minus omega cubed. This whole thing is equal to what? 0. And a complex number is 0 when both of the components are 0, which is these two guys. And guess what this one gives us? Yes, if you look at the bottom one, if you solve for omega from the bottom one, there are two solutions. One is, or three solutions. One is omega is 0 if you factor it out, and the other two are what? Plus minus square root 5. Correct? Omega 0 is not an answer for us because we know the intersection point. Actually, it is, because if you look at the, again, Root Locus, there is one other point also that the Root Locus will hit the imaginary axis, right? And that's here, at origin. So omega of 0 is actually a valid solution, but what I'm really caring is this one, which is a square root 5, and this one, which is what? Negative square root 5. So first, I found them, where they are. And then, if I plug in omega of 0 into the top equation, it gives us what? K equal 0, which of course it is, because in the Root Locus, I start from what value at a pole? Yes, k of 0. At any pole, k is 0. As I move toward zeros of that transfer function, which here I don't have any of them, so they're all imaginary at infinity, then k goes to infinity. So that's correct, that k here at this point where omega is 0, k is also 0. That's right. Now what about this positive, negative square root 5? If I plug them here also, the k for them is going to be what? Yes, 4 omega squared, which is 20. So that's what I needed. The location of intersections are plus minus square root 5, and the gain is 20. So what does it mean? For the system to be stable, k can ranges anywhere from 0 all the way to what? 20. Once I make k bigger than 20, now my poles are entering closed loop transfer function poles are now entering what? The right-hand side of imaginary axis, and system is unstable. So from this Root Locus, one of the first things that I can understand is for stability, what condition do I need? K between 0 to 20. And you probably notice I didn't use equal here, because if I do, then the poles are at the imaginary axis and the system is marginally stable. So if I want pure stability, they should be less than 20. Okay? Now, could I find this k using the Root-Horvitz method? Yes, absolutely. I'll do that for you here just as a practice. So what I would like to focus on is this equation here in green, s cubed plus 4s squared plus 5s plus k, and I show you that using the Root-Horvitz method, I should get the same criteria, k less than 20, with the system, although I don't need it here, but just as a practice. So if I go back and form the Root-Horvitz, so I have s cubed, I have s squared, I have s to the 1 and s to the 0, And if I go back and look at the coefficients, I have 1, 5, and 4k. So 1 and 5, 4, and k. And what is this coefficient, if you still remember? That's 20 minus k divided by 4. This one is 0, and that one is k. So we know that if we don't want any root on the right-hand side, there should be no sign change in the first column. Therefore, everything should be, because the first two are positive, everything should be positive. So this guy should be positive, and this whole thing should be positive. So what do I have? I have k should be bigger than 0, and then the numerator is bigger than 0, so k should be what? Less than 20. So you see the root Horowitz is exactly giving me the same thing. By the way, if I go back to this one here, I better correct it. So I should remove this equality here as well. Why? Because if I do so, then the pole is here, which is still on imaginary axis and means sustained oscillation. So I should keep avoiding the imaginary axis. Should be perfectly on the left-hand side. So the condition for stability in my case is what? K between 0 to 20, which I can find from Root Locus or Root Horowitz, from any of them, right? Okay, so now with all this info that I have, well, my Root Locus has 3 branches. They start at the points of what? 0 and negative 2 plus I and negative 2 minus I, and end up at zeros of the transfer function. In this case, I do not have a 0, so they should end up at what? As you can see here, they should end up at infinity. So let me put everything back together here for you, as this video is getting longer. So what I have is this is the real and imaginary axis. I have one pole here, one pole here, and one pole here. No zeros. Based on this info, I know that I have 3 branches. Then I have no zeros, so the zeros are imaginary and infinity. Good. Then what did we do? Then we found the location of the Root Locus on the imaginary, on the real axis. And we found that here in this example, this left-hand side of the imaginary, this whole thing is a location of a Root Locus. This is all valid. Then what did we find? We found the location of the asymptote intersection with the real axis and the angle of them. And if you go back to, where was it? Let's see, we had them plus and minus 60 degrees, and I guess negative 4 over 3, yes. Negative 4 over 3, and the angles were positive and negative 60 and 180. So if I draw them, this is negative 4 over 3. So these are my asymptotes, the guys in red. And these angles are positive and negative 60. Then we found that the breakaway points are at what? Let's go back and look. So they are at negative 1 and negative 5 over 3. So one of them is here. One of them is here, negative 5 over 3. Remember, this is negative 2 here. And this is negative 4 over 3, right? So this is negative 1. This point is negative 4 over 3. This point is negative 5 over 3. And this point is negative 2. So one of the places that the Root Locus gets off the real axis is this. One of them is this, right? So 3 branches. Here I have 2 complex, that's for the, yeah, so, and the angles of departure from the poles are what? If you remember, we calculated them, they were 63, negative, and positive. So what happens, and then I would hit the imaginary axis at the points of negative and positive square root 5. So if I draw them, one branch comes like this. It comes from 0, the first pole, to the breakaway point and then gets off. And as k gets bigger and bigger, ultimately it will fall onto the asymptotes. The other one is doing exactly different, right? So that's one of them. What about these two? So clearly you see we have to start from them, and then since everything on the real axis on the left belongs to the root locus, so one of them at angle positive, and let me change the thickness a little bit for you. Let me use a thick thing for the root locus. So the root locus, one branch is like this. That's one branch. Then the other branch goes from, let me use a different color. The other branch goes from this point. It exits at negative 63 degrees, comes hit here, and then goes to infinity. So one of them should go like this. And let me again make this thicker. And then the final one comes from what? It comes from this one as positive 63 degrees and then goes to this other asymptotes, right? So it goes like this. Goes to this breakaway point, and then what? Ultimately falls on this asymptotes. So there are 3 branches of root locus, and again this point is square root 5 and this point is square root 5 negative. K at each pole is 0, and each branch, as it goes to the imaginary 0 at infinity, k goes to infinity too. And we found at that point k was 20, and at this point also k was 20. So that is how we draw the root locus, which is exactly this guy here. Okay, so the good thing with MATLAB command is it colors each branch for you differently. So you see the blue, the red, and the green. Okay, so this is how we do a root locus. And these are the summary of items 1 through 8. And these are some of the typical root locus shapes that you might see. Now let's stop this lecture for now, and then I come back and we'll talk more about the location for constant zetas and omega n's, a little more on MATLAB, and we continue on this example because so far we have just drawn the root locus. We have to do a bunch more, and then we have to talk about systems with positive feedback and minimum phase a little bit.